All right, guys. So we just introduced the definition of a Laplace transform. And before we really start going through the nitty-gritty details as to how you can actually turn time domain functions using the Laplace transform into functions of the Laplace variable, there are two extremely useful and common functions that occur, not just in the differential equations that we're going to end up solving, but they occur in nature as well. And I want to take a little bit of time kind of as a sidebar to talk about these functions. The first function that I want to talk about is called the step function. The step function itself, we use the letter U to denote it in electrical engineering. Um, in physics, we actually use something slightly different. We actually use the Greek letter theta to denote this. But by definition, it can take on one of two values. The first value it can take on is 0, and the other one it can take on is number 1. And what it really truly depends on, whether it takes on the value 0 or 1, is what's actually inside of the arguments of the step function. So whatever happens to be inside of the argument, it can take on one of two values as well. It can either be a positive value inside of the argument of u, or it can take on a negative value. If it takes on a positive value, then whatever is making that function positive, it takes on the value of 1. And whatever makes that negative, it's going to take on the value of 0. So because here this happens to be a function of, right, it'll be 0 for argument less than 0, so for t less than 0. And the argument t is greater than 0 for t greater than 0, so it'll take on the other one, t greater than 0. Now, if you actually take a look at this closely, so for those eagle-eyed uh, engineers, notice that what we actually have there includes almost the entire real number line, right? We have less than 0 values for t and greater than 0 values for t. However, notice that there's one value that is conspicuously missing. There's no equal sign on those. That's what's actually happening to this thing um, at uh, 0, right? Uh, for mathematical reasons that lie a little bit beyond what we actually want, we're assuming that this right here is actually going to be a linear function. That means that it's actually going to take on the average value between 0 and 1 at 0 itself. So the one last thing, in the case that we actually need to evaluate it at 0, it is such that u at 0 is actually going to be the average of 0 and 1, and it's going to be 0.5, right? Now, this can also be represented graphically. So here, if we have t and f of t like this, then for all values greater than 1, it has a value of 1. For all values less than 1, it has a value of 0. Usually the way this is kind of denoted, right, is you typically also end up with the vertical line that's connecting that. And we really tend to not mention what's actually going on at 0, right? So, but this is what we actually have graphically. Now, two other important properties of this step function is the step function doesn't actually have to have that jump discontinuity from 0 to 1 at 0. It can also be shifted either to the right or to the left, right? So consider a shifted function, let's say of u of t minus a. And in this case where a can be positive or negative, but I'm just actually going to consider the case where a is positive. So this itself is a shifted step function. And one of the things that's going to end up happening is, well, wherever a happens to be, this is where the jump discontinuity in going from 0 to 1 is actually going to end up showing up. Right? So for all values less than a, it'll be 0, and for all values greater than a, it'll be 1. Why? Because, again, what I mentioned previously, whenever the argument is positive, the value of the step function is going to be 1. Whenever the argument of the step function is less than 1, then the argument is going to end up being, the function is going to have the value of 0. Right? So one last case that's actually extremely useful is notice that this moment, all of the values that are greater than a are 1, and all of the values that are less than a are 0. Sometimes we might want this to actually be kind of flipped around, to be the opposite, right? So one last case that might be actually useful. So this is, let's say, case number 1. Let's actually do this in green, just so that we can keep track of them. So let's say this is case 1. That's useful. Here we have case 2. This is the shifted step function. And then one last one that's actually useful is case number 3. So suppose that we actually had u not of t minus a, but let's say we actually had a minus t. Well, it should be very, very, very clear that the step function itself is actually going to have, once again, the discontinuity at a, right? So over here, just like we had a there, and again, we're going to make sure that a is greater than 0 for this example. We're going to have the jump like this, except because the argument here is now a minus t, for all values greater than a, the argument is going to be negative, which means that all these values are going to be 0. And if t is less than a, then all of those values are going to be positive, which means now that these values are now all 1. So it doesn't actually always have to be that this function is essentially positive to the right of some number. You could actually kind of flip it around, but you need to make sure that you have the correct argument. Now, one really interesting thing, and this is something that we're going to discuss in the next section, is if you actually take this step function, right? It is a continuous function except at the origin. What is the derivative with respect to time of this function? The derivative of the step function shows up absolutely everywhere in nature and also shows up in differential equations too. It's going to lead to what we call the impulse function, and that's actually going to be the topic of the next section.